Today I will introduce a method called EM algorithm. Basically, it's called the expectation maximization algorithm. And it's a brief introduction of it. It's developed based on the maximum likelihood estimation. Since MLE tells us that we should maximize the likelihood function to find the parameters data based on our observed value. However, in many cases, firstly, we have the missing data, which is difficult to write a whole likelihood function, the observed likelihood function. And secondly, we have a very complicated likelihood function, which is difficult to maximize directly. So, we introduce the EM algorithm, which provides a way to iteratively improve the estimation of data by introducing latent variables. Here, in each iteration, we need to find a group of parameter to make our conditional expectation of our complete likelihood to be the maximum. And we do this process over and over again until the parameters are convergent. Here the convergent means the k times estimation minus the k minus 1 estimation, their difference is less than a very small number, and this small number is defined by us based on our needs, such as 10 power minus 10, like that. And in this algorithm, firstly we need the observed likelihood function, where x the observed data, and also the complete likelihood function, which means we regard that the x and z, both the observed and unobserved data are all happen based, and we need this likelihood regard these two kind of data happen, and based on this our parameter. And here is a proof of EM algorithm, which tells that we need to maximize this expectation to make our likelihood function to be maximum. Hence, we just need to maximum is instead of this. And this is the EM algorithm. And since before the proof of it, we know that we know this equation, because this is just the probability of the observed to happen, and this is the complete to be happen, and this makes our this k, which is the unobserved data to be happen based on our observed and parameter. Since this integral equals to 1, we could directly write this as this form, and since this is independent of z, we could just move it into this integral. And based on that k, we could represent log L theta k, which is the log this as the differences of this, and expand this leads to this form. And this is by the definition of the conditional expectation. We write these two forms. And these are all expectations under the theta and x. Here, if we regard the t plus 1's iterative process, the result of our estimation parameter, as the parameters that makes this expectation to be the maximum, we have this relation since it is the maximum, right? So it's greater than anything, including this. And this tells us that this expectation increases by the iteration of theta hat. And if we look at, and actually this is just a form of this, right? They are the same. And now let's look at this. If this is just coincidentally, if it decreases by the iterations of theta, then we have proved. Now let's see whether it is true. Now by the Jason inequality, we could, when we move the expectation of something outside the, when we make log outside the expectation, we have this inequality. And by the definition of this expectation, we could write this as this form, and they are missing, and this leads to the integral as the 1. So log 1 equals to 0. So this term is less than or equal to 0. This means this is always smaller than this. So we have guarantee that this is decreases by the iteration of theta hat. So by the process of iteration, this likelihood function will become larger and larger. And if we make our estimation convergent, we have make our result of the estimation as a stable, which means, like we mentioned before, a very small number. And this means that we have maximized this likelihood function. Therefore, we just need to maximize this. So when we use the YAM algorithm, firstly, we need to write down the form of this conditional expectation of this likelihood completed likelihood function. Also we use some methods such as derivative and Newton method of our numerical analysis method to maximize this guy. And here's one example for the use of YAM algorithm used in the application of the censored data. Here, censored means if we have a timeline, and here we have the event to be successful or failure, but there is also some frequently happen things, which means we didn't observe this process fully. We just know on this timeline, such as this event is successful and from here, we just don't know whether the details of it. We just didn't observe it anymore. But if we just delete this event, it's kind of loss of information. This censored data is just the same definition in our survival analysis. And here, let's we denote that x1 xn1, this n1 x variable is identically distributions with the density of fx minus theta, and this is the nr n2 are censored observations that we only know zi is greater than or equal to a for some a which is known, and the observations are independent. And now we write the observed likelihood function and the complete likelihood function. Like what I have said before, maybe this is more complicated than this, right? If we want to maximize this, I think it's much more difficult than maximize this conditional expectation of this. Now let's see how this EM algorithm. First we write the P, which is what we place the expectation, and all conditional expectation is calculated based on this K. And since we know K, this is the complete likelihood function, and below is the observed complicated function, likelihood function, and this leads to the minus n2, and this has been deleted to 1, console to be 1, and we just this is the most concise shape of this guy. And we know that d and x are independent, and then we know that d1, these all unobserved variables are all independent and identically distributed random variables with the probability density function of this. Since it's all n2, and we just write this form as and since it's the n2 this, and from 1 to n2 this also n2, and it's all independent, so each of them is the product of so this makes us to know that the PDF of Z is just this form. Now let's write the E step. This is just we write down the complete function, which is what we have said before, is in this form, and by the definition of our expectation, conditional expectation is take on the K. So we expand this, we transform this as this shape, and since it's not relevant today, we move this outside the integral, and this since these are the same, since we all know that these Zi are all greater than equal to A, where A is known, so actually they are the same. So we expand this from this sum into this PDF, and then we have this, since this is 1, and we move into oxide. It's just expectation. So we know that it's this plus this. Now we write down this form. So we have deduced that the K, this PDF is like that, and this is taken under the key. So we write this as this guy. So this is each step, and we need to now we use the partial derivative method. That is equals to 0 to find our parameter. You just let this equals to 0. And it's another example for mixture problems. The mixture problems means like that. We have two kind of variable. One is the one distribution, another is another distribution, such as this example. This is exponential of 1 over theta 1 and exponential of 1 over theta 2, and W follows the Bernoulli distributions, and this is where our missing data comes from.